Everyone loves to talk about how powerful quantum computers could be, but very few people talk about the villain of the story, decoherence. It's the reason quantum computers are so hard to build, so hard to scale, and so easy to break. So, what is decoherence? Let's start with the basics. A quantum computer stores information in qubits, which are incredibly fragile quantum states. These states rely on superposition and entanglement, the very things that give quantum computers their power. But here's the problem: quantum states don't like being disturbed. Any interaction with the outside world, heat, vibration, stray electromagnetic noise, even tiny imperfections in the hardware, can knock a qubit out of its quantum state. When that happens, the qubit loses its quantum state, and the process is called decoherence. So why is decoherence such a big deal? In classical computers, a bit is either 0 or 1. It's stable. You can bump your laptop, heat it up, run 100 apps, and the bits will still behave. Quantum bits, on the other hand, are more like soap bubbles floating in a hurricane. If a qubit interacts with anything, even the environment itself, the information collapses. And once it collapses, the quantum computation fails. It doesn't just give you the wrong answer, it destroys the entire process. So, how fast does decoherence happen? This is where it gets wild. Some qubits stay coherent for milliseconds, some for less than a thousandth of a millisecond. To put that in perspective, a classical CPU can perform billions of operations per second. A quantum processor has to perform an entire algorithm within the tiny window before decoherence ruins everything. This is why quantum error correction is so important. Without it, real quantum programs would fall apart almost instantly. So how do engineers fight against the universe trying to destroy their qubits? They use extreme engineering. Superconducting qubits need temperatures colder than outer space, around 15 millikelvin. Ion traps use electromagnetic fields to levitate individual atoms in a perfect vacuum. Photonic qubits need ultra-pure optical pathways with almost no loss. And even then, decoherence still happens. We're constantly pushing the limits of physics to extend coherence times just enough to run meaningful algorithms. Why does coherence make quantum so hard? When people ask, why don't we have large-scale quantum computers yet? The answer is simple. Decoherence is relentless. Until we can protect qubits long enough, quantum computers will remain some of the most challenging machines ever designed. But that's what makes the field exciting. We're inventing entirely new ways to control nature at its most delicate level.